You've seen them, right? Those colorful spray paint lines that show up on the sidewalk right before a construction project starts. Well, they're not just random graffiti. They're actually the last chapter in a pretty amazing story of technology and detective work. So let's dive into this hidden world and really uncover the science of utility locating.
It all starts with professionals like this one. These are specialists who use some seriously sophisticated tools to see right through solid ground. And their job is absolutely crucial. They have to map out that complex, invisible infrastructure that powers our modern lives before a single shovel even thinks about breaking ground.
That's the million-dollar question, isn't it? We're literally standing on top of this tangled web of critical lifelines every single day. So how in the world do you make that invisible world visible? How do you dig without accidentally plunging a whole neighborhood into darkness?
To answer that, first we've got to appreciate what we're actually dealing with. Let's talk about the invisible underground. The sheer scale of what's hiding just beneath our feet is, well, it's pretty staggering. I mean, really think about it. Just inches below where you're standing, there's basically a bustling metropolis of pipes and cables. Hitting any one of them can cause massive disruptions, dangerous leaks, or super costly outages. This is why finding them accurately isn't just important, it's absolutely essential.
All right, so one of the main tools in a locator's toolbox is electromagnetism. The basic idea is to make a hidden pipe or cable sing a specific tune that a special receiver can then listen for. Let's break down how they do it.
There are really two main ways to get this done. First, you've got the conductive method. This is literally hands-on. A transmitter gets clipped right onto an accessible part of a metal utility, like a valve or a meter, and it sends a specific frequency shooting right down its length. But what if you can't physically touch the pipe? No problem. That's where the inductive method comes in. The transmitter is just placed on the ground above where the utility is supposed to be, and it induces a signal onto the line from a distance. Think of it like wireless charging, but for a pipe.
Now, just getting a signal isn't enough, you need a clear one, and that takes real precision. It's kind of like tuning an old radio. The orientation of the receiver is everything. As you can see in this diagram, you get the absolute strongest peak signal when the locator's antenna is perfectly perpendicular to the utility. If you're off by even a little, that signal gets weaker, making the target way harder to pinpoint.
So how do you make sure you don't miss a pipe that's running at some weird angle? Well, you perform what's called a four-way sweep. By walking the area in a grid pattern from multiple directions, operators make sure their receiver is going to cross every potential utility at that perfect perpendicular angle at some point. It's a super systematic approach that guarantees 360-degree coverage.
Okay, but that electromagnetic stuff works great for metal pipes. What about plastic? Or what if you just want a more visual picture of what's down there? For that, we turn to a technology that's basically an ultrasound for the ground. Ground Penetrating Radar, or GPR.
The concept here is brilliant, and it's pretty simple. The GPR unit sends a pulse of radio energy down into the ground. When that energy hits something different, like a pipe or even just a change in the soil, some of it bounces back to a receiver. By measuring how long that echo takes to return, the machine can build a picture of what's below. And the huge advantage here is that GPR doesn't care if the target is metal, plastic, or even an empty space. It sees it all.
So what's an operator actually looking for on their screen? This right here, the hyperbola. Because the GPR antenna sends out energy in a cone shape, it starts to see the pipe before it's directly over it, as it passes over, and then for a little bit after it is passed. That whole journey creates this classic inverted U shape in the data. So the bottom line is, a hyperbola means you've probably found a target.
And here's what that looks like in the real world. This is an actual GPR scan. You can clearly see multiple hyperbolas stacked at different depths. Each one of those arcs represents a separate object buried down there. The peak of that U, the very top, that's the money shot. It marks the exact location and depth of the utility.
And get this, GPR can even offer clues about what a utility is made of. A metal pipe is super reflective to radio waves, so it creates a very bright, strong hyperbola, just like the one on the left. But a non-metallic PVC pipe, on the other hand, isn't as reflective, so it results in a much dimmer, weaker hyperbola, like you see there on the right.
So we've got all this amazing technology, right? But using it effectively isn't just about pushing a button. This is where the science meets the skill of the operator. Because, the real world is messy.
Operators face a ton of challenges out there. Wet clay soil, for example, can just absorb a GPR signal, which really limits how deep it can see. In a crowded city street, signals from one pipe can bleed onto another, causing a ton of confusion.
Trying to find plastic pipes that were buried without a tracer wire, that's a special conductive wire, can be incredibly difficult. And even something as simple as a nearby cell phone or radio can create static and noise in the data.
To get the depth measurement just right, operators have to calibrate their machine for the soil itself. They do this using something called the dielectric constant. The best way to think of it is as a speed limit for radar waves. Different materials, like wet clay or dry sand, have different speed limits, and if the operator sets the wrong speed limit in their machine, the depth calculation could be off by inches or even feet. Getting it right is absolutely crucial. This is exactly why it's such a skilled trade. These operators are constantly interpreting data using multiple senses. They're watching the numbers on the display for signal strength, sure, but they're also listening. A lot of these locators emit an audio tone that gets higher in pitch as you get closer to a target. It's this combination of sight and sound that lets them truly understand what the machine is telling them.
So, after all this science, and all this skill, and all this sweeping, how is this complex underground map actually communicated to the construction crew? Well, it all comes down to a simple, universal language.
The final result is these lines of spray paint. And, like I said, they are not random. Each color has a very specific meaning, and it's all dictated by an international color code. It's a visual shorthand that everyone on a job site can understand in an instant.
And here's the decoder ring for that code. Red is for electric. Yellow signifies gas or oil lines, definitely one you want to be careful with. Orange is for communications, like fiber optic cables. Blue means potable drinking water, and green is for sewer and storm drains.
All of this information then gets compiled into a detailed field map. This document is the culmination of all that work. It's a clear, precise guide that shows an excavation crew exactly where they can dig safely. It protects billions of dollars of infrastructure, and more importantly, it protects lives.
So the next time you see those colorful lines on the pavement, you'll know they're not just paint. They are the visible evidence of an invisible world brought to light by this fascinating blend of physics, technology, and pure human expertise. What new details will you notice now?